On the screen right now are three simultaneous equations with variables x1, x2 and x3. Would you be able to solve this problem and find the value of x1, x2 and x3? I'm sure you can do it. You can do it in just 3 minutes. This problem is easily solved using simultaneous equation elimination method. And that is the answer. We can do this calculation because we are trained to do that in secondary school. That is human ability. But we are facing a problem to teach a computer to do that, especially using simultaneous equation elimination method. And why is that? Because computer is dumb. We need to give computers specific instructions, step by step, to solve simple mathematics like this. Computers need algorithm that software engineer can easily code into a computer. There are many algorithms invented over the years, and these are 4 of them. And we are interested in LU decomposition and in particular Crout's and Doolittle's method. And these are the 3 simultaneous equations again. We need to have a system that we can put these 3 separate equations into one. The algorithm works best if we can put these equations into a product of matrices like this. I hope your knowledge on matrix is still tip-top because we'll be performing multi-dimensional matrix multiplication in the upcoming exercises. We call this matrix A. Matrix A consists of coefficients from the 3 simultaneous equations. Take a brief look between the item in the matrix A and the 3 coefficients of the simultaneous equation. Can you see it? And then, matrix X consists of the 3 variable X. Eventually, we'll be finding their respective values, and that is the whole objective of Crout and Doolittle's method. Then we have matrix B. Matrix B consists of the numbers on the right side of the simultaneous equation. So, we can write the product as AX equal to B, and we will be solving for matrix X. And in the following, I will show you the concept of LU decompositions. They might look a bit cryptic, so you might need some time to digest the information. We want to decompose matrix A into 2 matrices called L and U, and that is the reason for the name of LU decomposition. L is a lower triangular matrix and U is an upper triangular matrix. Okay, I admit, the information does not help you that much, but bear with me, I will explain. This is matrix A, the matrix of coefficient, and this is matrix L and U. Notice the triangular shape in L and U. L is said to be a lower triangular matrix because the lower part of the triangle has numbers in it, while the upper part has zeros. And U is called upper triangular matrix because the upper half of it has numbers to be evaluated, while the lower half has zeros. And notice the slanted number 1 in red in matrix U. While this one looks very similar but a bit different. Notice that the slanted 1 in red is within the matrix L, and this is called Doolittle method. You might be asking a question, what is the purpose of decomposing matrix A into L and U? Well, it is not easy to answer verbally except by saying that triangular matrices have special properties in converging into a solution. Perhaps after the whole exercise, it will become evident why it is so. Our problem is not over yet. We will be introduced to another matrix, a vector matrix called Y, a small letter y. Matrix L, U and Y are just a placeholder matrix with a sole purpose to help and store temporary data as to assist us in getting to the solution of the simultaneous equations. Now watch this. We started by putting the 3 simultaneous equations into product of matrices. Then we perform LU decomposition. So because A is equal to LU, then LUX is equal to B. And then we assign Ly to B, and Y is the matrix I just mentioned a few seconds ago. So now Lux is equal to Ly, and since L exists on both sides of the equation, we can cancel it out. So now left with Ux equal to Y. And this is the last step. We'll be solving for X in this step. We'll be doing that using Crout's and Doolittle's method, and Crout first. For your information, Crout's method was invented by American mathematician, the late Dr. Prescott Turan Crout. First, we do LU decomposition. So now A is equal to LU, and then multiply L by matrix U, then it gives us generic matrix like this. And now we compare each element of the matrix on the left by that corresponding elements on the matrix on the right, so that we can find the value of each element in matrix L and matrix U, and that is our objective in this step. So we pick up the one that's easiest to solve, and that is the pair over there. And with that, we are able to solve the first three elements of matrix L. So we update the matrix with the three components of L, and we pick up the next pair, the easy one. These two pairs, and that gives us L22 and L32. And this pair gives us U23. And now we are almost done. There's only one element left in matrix U. The last pair gives us L33. We are done with LU decomposition. And that was rather quick, yeah? Because this material was pre-prepared. But the actual work is rather lengthy, tedious, and error-prone. So if you are doing this, make sure that you check everything, all the numbers and the symbols are correct. You want to avoid silly mistakes, because one small mistake will make the result, everything go wrong. So this is how the completed LU decomposition looks like. We have already derived matrix L and matrix U for Crout. Now we are ready for the next step. The next step is to assign Ly equal to B. So this introduces another vector called Y. And this is vector L, and this is vector B, and we put them together, and it becomes like this. And a vector Y is a 3 by 1 matrix. We then multiply L by Y, and because L is a lower triangular matrix, it is easier for us to go and solve for Y1 first. So, multiplying the top row of vector L by that of Y, then we get the value of Y1, which is equal to 2. So the next one, the second row of L multiplied by Y gives us an expression or an equation of Y1 and Y2. But because Y1 is already known, then we get the value of Y2 pretty straightforward. And now, off to the last variable, Y3, multiply the last row of L with Y, and that gives us the 3 variable equation. Since Y1 and Y2 are already known, then we get the value of Y3. So now that we have solved vector Y, so this is how the completed multiplication look like. We are going to use vector Y for the next process. The last step is to equate Ux equal to Y using vector Y that we have just derived. This will eventually solve it for X. This is our vector U, vector X, and at the corner over there is vector Y. So let's do that multiplication. The last row of vector U multiplied by that of X, then we get that expression, and we get the value of X3, which is equal to 4. So we've got the solution of the first variable, which is X3. Next is X2. Now by multiplying the second row of vector U and vector X, then we have a 2 variable expression or 2 variable equation. Since X3 is already known, then we can find out the value of X2. And lastly, variable X1. By multiplying the first row of U by vector of X, then we get a 3 variable equation. Since X2 and X3 are already known, then we can solve easily for X1. And now we have completed Crout's method, and that is the value of X1, X2, and X3. And if you check this with the simultaneous equation elimination method, then you find out that the answers are exactly the same. The process is very tedious, but the algorithm is the most efficient one that we can implement on the computer code. And now we are doing the Doolittle's method. And do not believe in the name, yeah? The name Doolittle does not mean that the work is going to be little. In fact, it's going to be exactly the same amount of work to be done. I believe Doolittle is the inventor of this method. We'll begin with LU decomposition, and this is how it looks like. Note that now the slanted one in red are in matrix L. Now we multiply matrix L by matrix U, then we get this generic expression. The next step is to compare each element of the matrix on the left with the respective element of the matrix on the right, so that we can find the value of L and U individually. and always begin with the easiest pair one, and the easiest pair is that one, and that gives us U11, 12 and 13. We update the matrix and select the next pair, and that gives us the first two elements of matrix L. Next, pick up the next easy pair, and that gives us U22 and U23, and we are getting closer. And next pair, we get L32, and the last one, we get U33. And now, LU decomposition is complete. And this is the completed LU decomposition Doolittle's method. We are not done yet. As we have done in Crout previously, we need to introduce vector y by assigning Ly to B. And this is how it looks like. And since L is a lower triangular matrix, it's easier for us to go and solve what? Y1 first. By multiplying the first row of L with y, then we get that equation, and straightforward, we'll get the value of y1. Then we do that for y2. y1 is known, and we get y2 equal to minus 2. And the last one, y3, since y1 and y2 are already known, then we get the value of y3, and we are done with matrix y. We are going to use matrix y in the next process. Our final step now, ux is equal to y, using vector y that we have just derived. And because matrix U is a lower triangular matrix, then we start with x3 first. By multiplying the last row of matrix U by matrix X, then we get the expression. And since there is only one variable there, x3, then we get the value of x3. So now, we have solved the first variable for x, which is x3. Next one is x2. From the second row of matrix U with matrix X, then we get a variable or an equation with two variables, x2 and x3. Since x3 is known, then we know, then we can determine the value of x2. And lastly, x1, by multiplying the first row of matrix U by vector x, then we get that expression. Since the value of x2 and x3 is known, we get the value of x1 there. And that is the solution, the value of x1, x2 and x3 there. If you compare that value with the one that we get from Crout and from the simultaneous equation elimination method, the values are consistent. As you can see from the result, Crout and Doolittle give us the same result, so they are consistent. They are both tedious to handle, but it is the most efficient to be implemented on computers. And in fact, computers with this algorithm can solve simultaneous equations of perhaps 10, 100, 1000, even 1 million simultaneous equations, and that's how powerful these algorithms are. I like to encourage every one of you to research this topic over the internet and libraries. With this skill, you can become an awesome mathematician with an inclination to computer programming if you master this topic. Thank you for your time and interest. Make sure you watch another video so that you can get more knowledge in mathematics. See you. Bye-bye.